We're live.
We're live, and welcome to another episode of Labs Talk.
Yeah, welcome to the first episode of Labs Talk out of our new studio that you can see here on screen. So
we're supposed to sound a lot better, do we?
Yeah, I hope so. I have to remind myself to speak into the microphone, but I think we're good. So
that's a new one indeed.
And we have an amazing guest. So our show is all about quantum computing, superposition, entanglement, all the other things. And we have the perfect guest, Isabel from TU Munich.
Thanks a lot for having me.
Thanks so much for being here.
Isabel, before we go into your topic with quantum computing, Sven, let's spend 1 minute. We're always doing this as a series, and we always start with a brief recap before we go into a new topic. What was the old topic? What did we talk about the last time we met?
Trying to put me onto the
any time, sir.
Yeah, so the old topic was esports with Sandra, right? Sandra Bloy. And I think she is the president of the Bavarian Esports Association, right? Kind of cool. I mean, for me, this was a whole new world to explore. And yesterday at OMR, I was at OMR yesterday, yes. There was a lot of talk also about esports and crypto, to be honest with you, because it's kind of used a lot for in-game payments and stuff like that. So
Sandra didn't talk about crypto.
No, she didn't talk about crypto, and in general, I would say crypto is also dead basically right now. Although I mean, there's still a big fan base, but it's not a hyped topic right now, right? The hyped topic is AI.
Wait a second.
And
I still have this sticker for you.
What is it?
I think it's some crypto something.
Cyber. I will not say it actually because it might be advertisement, right? But it's a cool sticker. Thank you so much, Andreas, for this present that I get in the show. But we have an even cooler topic today, right?
We spoke about esports a lot.
Yeah.
So if you're curious, cool episode, lots of insights.
Yeah. And if you're older than 30 years old or so, then it's an episode to really watch because you will learn a lot about esports. For me, it was a little bit like a foreign world, to be honest with you, because I'm not sitting daily in front of my laptop and play hours of games, right? But was good learning, really.
You do, come on. I know you do.
I'm just tapping these stupid games, but yeah. Anyway.
Now one final sentence before we come to you. We're going to talk to you about crypto and your research.
Quantum.
I just wanted to say, wait, am I a new expert in crypto now?
No, you're not. We had other experts in quantum computing already, and we did scratch the surface a few times. And now we felt like we need somebody like you here. And we spoke to a colleague that does quantum computing for fun. That's Anish. Big shout out.
Yeah,
and we
also
spoke
Andre, right?
To Andre, who is actually a quantum researcher. It's going to be a hard episode.
Yeah.
He's a researcher. We're going to speak to Andre in the next episode.
Nice.
But today we will have you as a guest. Once again, thank you for being here. And we met you because you give this quantum one-on-one courses. Let's maybe literally start and hand this over to you. Maybe you want to introduce yourself and talk a little bit about the motivation, everything that got you into this.
Yeah, sure. So I'm Isabel. And as you said, I'm a PhD candidate exactly in this field, in quantum computing. I personally work mostly on the software side, but actually quantum computing is about everything related to this new technology. And we will talk about this a little bit more in detail, right? So you have a hardware side, basically, but also a software side. I'm more focused on the software side. So maybe what is a quantum computer? So what do I do in my everyday life as a researcher? Quantum computers are basically this new type of technology that is based on quantum physics. So maybe you should also know that I studied physics. I'm not a pure computer scientist, but the nice thing about quantum computers are that you, even as a physicist, you can now think about how to make use of this knowledge from quantum physics to build a new type of computer. I think that's actually super nice because usually if you study physics, you just try to understand how the world functions. And then at some point you might maybe find out, oh, you can build a laser with this knowledge. You can actually apply this, and it will have some impact on everyday life.
Everybody understands lasers.
But at least a lot of people use lasers. And with quantum computers, you can try to just make use of this knowledge to build this new type of technology. I think that's super nice.
So let's stay with the problem areas of quantum computing. So, I mean, if you try to invent a new area, a new kind of computer, they must be good for something, right? So better than classical computing that we probably know. So what are quantum computers especially good at?
Yeah, that's a very valid question. And I think there are various fields where you have very complex problems, very complex maybe simulations that you want to run on your computer. And most of the times you are kind of limited in either time or memory. That means that your classical computer might not be able to solve these problems. And quantum computers in some areas could help with that. So for example, what a lot of researchers are interested in is the aspect of simulating complex systems, for example, chemical systems, molecules, something like that. Just because if you want to simulate something like that, you need to take into account a lot of degrees of freedoms. And this is super difficult for classical computers. Whereas a quantum computer might be capable of dealing with all these degrees of freedoms. This is one potential application field. Another field is, for example, cryptography. So I think one of the most famous quantum algorithms is the so-called Shor's algorithm. You don't need to know how this works, but basically what you could do with that is you could factorize an integer in polynomial time, so in short times in comparison to what a classical computer can do. And by doing so, you could break current encryption schemes, which means that this is, of course, something you should worry about. Therefore, you can now think about how to maybe make use of a quantum computer to do quantum safe encryption. This is another field.
I just wanted to say, like, okay, so now the main motivation behind quantum computing is trying to break cryptography. No, of course, there's a positive aspect to that, right? We're trying to make it quantum safe now, right?
Yes.
So there's quantum safe cryptography, which saves the world. Right? No.
If you want to say so, yeah. So I think another application field that a lot of people also maybe from industry are interested in is optimization. So
we sure are.
Yes. So
and we will have guests to talk about the problems that may require quantum.
Exactly, because within optimization, there are so many complex problems, and basically everywhere there are optimization problems, right? So in industry, if you look at supply chains, etc., this is highly complex. And I don't want to state that a quantum computer for sure will solve these complex problems, but there's active research and there is a hope that this could be a valid application field.
So will at some point quantum computers then take over and our classical computers, like our smartphones that we know and the computers we have in front of us, no longer play a role, and we'll just have quantum computers that are small enough to fit into a laptop? Or will this be a technology that's kind of adjacent to classical computing?
Yeah, that's a good question. I get this question quite often, actually. So how I see it is that, and I think that's how everyone basically sees the future, is that classical computers and quantum computers will go hand in hand. So as I said, there are these certain application fields where a quantum computer can do stuff or will do stuff that classical computers might not be capable of. And for this part, we can use the quantum computer. But if you, for example, just want to watch some YouTube video on your cell phone, there's nothing quantum that needs to be involved. So I think never that, like, even if we have a quantum computer that can solve these complex problems, most of the things that we do nowadays on a laptop will still be done by us on a laptop in the future.
Okay, now, cool. With everything you just said, maybe we need to do a little bit more research again, but one of the reasons we re-entered this entire topic of quantum computing have basically been a few announcements that came out late last year, early this year.
There was
just before this show, we spoke about this announcement that Microsoft made about their Majorana chip, and I think
well
Google,
pronounced. Thank you.
It's probably not the pronunciation, but there was an announcement about a chip. I think that had quantum built in, and Google made an announcement. There have been a series of announcements that involved quantum computing one way or another. Miniaturization definitely played a role in that announcement.
And error correction, by the way, right? Increased error correction. I remember that correctly.
All of these, it may not have been the actual news, but just the amount of headlines that came out at least suggest and indicate there is some sort of normalization in quantum computing. How does that match together?
Yeah. So I think what you referred to with the Majorana announcement was something that Microsoft does research on. So in quantum computing, you want to build a quantum computer on the hardware side, and there are different ways to build such a quantum computer. So there is not that one way to design a chip. Microsoft focuses on this Majorana particles, and they announced that they basically had a breakthrough when it came to that, because this is a very, very new research field. Actually, there is not a lot of results yet, and I think the announcements maybe sometimes sounded very, very huge. And if you are not in the research field, it sounded like, oh, they really got something like a device that works on the basis of a Majorana particle. Let me maybe debunk this a little bit, because I think it was for sure a big step for them in their research field. But as I said, this research field is very, very novel. So they did not bring out a quantum computer based on this hardware platform. This did not happen. But they detected something that they think could be the basis of such a quantum computer, which suddenly sounds much less exciting for someone who just waits for the actual quantum computer. But I think it was nevertheless exciting for the researchers. And then when it came to the other announcement with the quantum error correction, that one was very exciting, actually, because quantum error correction is a very, very important aspect in quantum computing. What does it mean? It basically means that if you build a hardware, it is very noisy. It has a lot of errors. Your calculation will be wrong, basically, at some point. And in order to correct these errors, you need this quantum error correction, which is a very big component of building a big quantum computer that functions well. And what I think Google released this announcement, what they did was they could fabricate, or they could show that their quantum error correction scheme on their hardware actually worked out in a way that they can scale it to larger systems. And that's actually a very, very important aspect when we look at future quantum computers.
They released a chip, I believe, right?
Exactly.
And just maybe one very stupid question about this chip. Would that be a chip that you can put onto a normal PCB, a normal platine, basically a normal board? Or is that something that would only work in a cooled down minus 250 degrees, whatever, Celsius, Fahrenheit room, basically? So just out of curiosity, is that a chip that everybody can just use? Or is it a chip that's highly specific to quantum researchers?
So this chip that Google released is based on superconducting qubits, or superconducting like building blocks, which means that it actually has to be cooled down a lot.
Okay.
But in quantum computing, there are these different hardware platforms, and some of them do not require this cooling. So this is very specific to the Google hardware that they released. Yes.
Okay. So now we're entering the depth of quantum computing, because we already talked about, I just learned something, Majorana, which seems to be something that is as small as a qubit, or maybe smaller, I don't know. But we're entering qubits, right?
Yeah,
I guess.
Same for me. You mentioned that. I know that term has been around, but let's take that as an opportunity and really go into the depths of the technology, I guess. Maybe you can explain, you can help us and our audience to understand those, how essential qubits are for the technology, and to
And what it is, right? I think it's the smallest element of a quantum computer, or of a
if you want to say so, you could say that. Yes. So okay, maybe for the computer scientists or people that are used to classical computers, you maybe know that you can basically encode your information into bits, right? Into these zeros and ones. And then these qubits, they are just the quantum equivalent to the bits. So it's like the smallest unit where you can encode your information. And in our case, a qubit is basically just some quantum system. So that sounds scary. But what it basically means is that you have some quantum system that you can control in such a way that you can store and process your information with this.
Yes. Apologies for interrupting. It's because you said information. Like, I'm a computer scientist. Like when I think the smallest piece of information, I think 0 and 1.
Exactly.
And
that's
qubits
the case
are different.
Right? Yes, exactly. That's a very good point, and that's also the big difference in general between quantum and classical computers. In your classical computer, you have the information 0 or 1, and in the quantum computer, your qubit is more complex, so it's capable of storing more information. And this is something that comes from quantum physics. It's a concept of superposition. So it's basically the superposition of your information 0 and your information 1. I think I have this Bloch sphere that could visualize that.
Let's
right?
bring that on, actually.
Exactly.
So I've got it here in the.
That's here, right?
Yeah, I will just add it to the screen, and
so for everybody trying to figure out what we're doing here, we don't have that screen in front of us. We're working with notebooks.
Yes, but now we see the Bloch spheres. Okay, so I mean, you can watch your screen and I can watch mine.
Yes.
And then maybe just before you go into the Bloch spheres, the way I also visualize qubits right now, in classical computing, 0, 1 is like a switch that you turn on and off. So it's basically, it points up or it points down, basically. For me, the Bloch sphere is, in this case, 3-dimensional object, and more or less it has a direction, right? And it can, that's why what you maybe also mean with superposition, it can be pointing in any direction at the same time too.
Yeah.
And that makes it a bit more complex. It's between all these states that it can.
I think what you just mentioned with your bit just pointing up or down is exactly what I tried to visualize in the middle of this, or in the center Bloch sphere. So basically your Bloch sphere is just this one sphere. And then if you had a classical computer with a bit, you only have 0, which could, for example, be an arrow pointing up, and 1, which could be an arrow pointing down. And with a qubit now, you could have the arrow just pointing anywhere on this whole sphere. So you have infinite possibilities, basically.
So it's not just up and down and like the 3 p.m. and 9 p.m., but it's also forward and backward.
Exactly.
And everything in between. Okay.
Exactly. Yes. And that's one of the main things. So our qubit can store more information, if you want to say so.
And superposition is then, if I mean, I looked it up, right? So it means more or less it can be any state in between these states, so to say, right?
Exactly,
so
yes.
That basically means, is it kind of spinning or rotating, and we never really know what it is, basically, unless we kind of stop it, right? Or what is how does this work, basically?
In this Bloch sphere picture, you would just have one arrow, so it does not have to spin. If you have one state, it can just be some arrow that does not move. But since it's not pointing up or pointing down, but pointing somewhere, it's like a superposition of the 0 and 1 state. But I think I know what you're referring to when saying, oh, you need to kind of measure it, because the superposition in general is a concept from quantum physics. And you often, for example, I often use this coin that I brought here to visualize that. So if you imagine you have a coin and you have head or tails, so that could be your 0 and your 1. If your coin just shows heads, then you're in the state 1, for example. But now if you throw your coin, and I will not do it now because otherwise I might not be able to catch it. But if you throw your coin and it's in the air, it's rotating maybe, it's spinning maybe. It's some kind of superposition of heads and tails.
Okay.
But now what happens if you catch it again, if you're able to catch it? You can imagine it as some kind of measurement. So you will catch it.
That's the measurement.
Exactly. Look at it. So is it now heads or tails? Now it has a definite state basically in this one or.
I remember that famous experiment from when I was in high school. They had experiment with that cat in a box.
Yeah,
so
exactly.
You would never know in which state it exactly is, unless in this case that coin you wouldn't know unless you catch it.
Exactly.
And when you catch it, it's fixed somehow. It's either head or tails.
Exactly.
And so Schrödinger's Katze, right? That's what you're referring to. And we talked about it in the pre-chat. I think it means like you put a cat into a box plus some poison, I believe, right?
Yeah.
And you never really know in what state the cat is unless you open the box.
Exactly, like state of dead or alive.
Yeah,
exactly.
dead or alive,
Yes.
exactly.
Exactly.
So now remember that Schrödinger's Katze if you want to talk about Quantum 101.
Yeah, that's
in
correct.
the evening when you meet your peers, whatever. So Schrödinger's Katze. Okay, so there's another concept that we have to talk about, and that's super crazy, of course, right? That's entanglement. Okay, so there seems to be a way to connect two qubits to each other.
Yes.
And then you can if I understand it correctly, you can physically separate these qubits. And if you turn one qubit, like let's say from the 1 state to the 0 state, or to the forward backward state or so, the other qubit will react, right?
Yeah.
And also turn. So that is very challenging, but it seems to be physically somehow explainable or working this way. It's just a physical
so
phenomenon. Or,
this entanglement is super, super interesting since. So I at first couldn't believe that this could actually happen. But this is also a concept from quantum physics where exactly what you said, you can we say entangle the states of 2 qubits or even more qubits. You could do it for n qubits. And then if you just manipulate the state of one single qubit, all the other qubits that are entangled will immediately change their state in a predictable way, basically.
Okay.
And it's not like these qubits need to be more or less in the same box, more or less, or in the same space.
No, it could be somewhere on the moon, basically.
But for the entanglement, you have to put them together, and then you can separate them.
Yeah. Exactly. So if you want to create your entanglement, it needs to be like locally close to each other, and then you can do some crazy stuff. Suddenly it's entangled. But after they are entangled, in principle, you could move them very far apart. This entanglement is very fragile, so you need to be super, super careful. So it's not trivial at all. But in principle, you could just put one qubit here and one qubit in Stuttgart or somewhere.
Okay.
That's the amazing thing for me is that this is real science, right? This is not like like believing in the aura of stones or something like that, right?
No.
So this is the stuff that is real, basically, right?
Yes.
There are researchers. It's not that they don't just believe in it; they have proven it, right?
Yes, and it's also nothing new. So it's nothing new.
Yeah,
so it's been investigated for centuries. Yes.
Why is entanglement important? What could it enable, for example?
Yeah, so I mean, if you have several qubits that store information and you want to manipulate this information, you now do not have to manipulate each single qubit. You can, in principle, just manipulate the state of one qubit and immediately change all the other states, basically. So that means it allows you an immediate transformation of several information. And this is, of course, a great help if you, for example, want to search a very big space for some good solution.
Okay.
Does it also, like in particular, since you talked about these qubits can be moved, transported to a different place, and they're still entangled, can that be used for communication?
Yes, this is actually also an active research field, quantum communication. This is a little bit of a separate research field in comparison to quantum computing, but yes, you can for sure make use of this concept to also encrypt your communication, for example, but also to enable the transferring information for communication. Yes.
And so what I was looking at in combination with that was how can you, with that entanglement and superposition, I think there's a way you can also stop people from eavesdropping on your communication, right? You can more or less create really safe communication channel. And even if someone would actually listen to that channel, it would immediately not work anymore. And you would basically be notified that something is wrong. Someone might be trying to intercept you, right? So why is that? Why? So I think it's based on 2 qubits that you entangled, right? Let's say, and then let's say you quickly switch the qubit 1 into 0, 1, 0, 1, 0, 1. Okay, let's just stay in the easy 0, 1 world, basically, which is also possible with qubits. And that could be the signal that you want to transmit, right? And if someone would try to eavesdrop on that, basically intercept it, it would not work anymore. Why is that?
Okay, so I think how to break this down. So if you have a qubit, and I already said you would have some state. If you measure the state, you collapse the state. So you suddenly don't have the superposition anymore, but suddenly you have head or tails. So this means if you have 2 entangled qubits and you measure 1 qubit, you will immediately also affect the other qubit. And I think the idea behind this encryption scheme is that you know for sure if nothing happens to your qubit, then there will be some certain measurement outcomes or some statistics that you can collect. And you know for sure, due to this entanglement, if someone interfered in between, then your statistics will look differently. So I think it's a little bit difficult to break it down. But in the end, the idea is that the information that you can gather from your original qubits that are entangled will be for sure different than the information that you can gather if someone interfered in between, since these are.
And it's something you can safely measure or figure out, basically. And that's why it could enable very safe communications at a long distance.
Or tamper-proof communication as well. Like when you try and figure out the communication channel, it will impact. It will be observable on the other end.
Should we go just one level deeper now? I think when I look at our script or at our, not really script, our pre-chat, basically, I think we go a little bit deeper, right? And then we go up again. It's getting a bit easier again. But the one more topic that we want to cover is quantum gates, actually, right? So we have a rough understanding of qubits, right?
Is that the level deeper, like from the conversation we had before? That's entering those territories that I remember, like when computers operate with logical gates and everything. I think that's up the stack that we're getting to. But go on.
I mean, I just want to speak in terms of complexity, I think, right? We're just adding one more concept now. Down there are quantum gates, and I know there are logic gates and stuff like that in classical computing, but here we just don't have something like and or, but we have something beautiful such as Hadamard gate, for example, or as, I mean, C-Not gate, I believe that might exist very similarly, right?
I don't think it does.
It doesn't.
I think that's an extra one.
But it's kind of it's easier to understand. So that and just wanted to kind of come to the point that these operations or these gates that exist in classical computing also exist in quantum computing, but here now it's just way more complex, right? So
yeah, that's true. Because as we discussed before, in quantum computing, you can also have 0 and 1s, just as we have it in classical computers. That means that everything that we can do with these 0s and 1s, we can also do with a quantum computer, which means that the logical gates that we have in classical computers, yes, they do also exist in quantum. But in addition, since we now have these qubits, so these superposition states, we also need more gates, or we have access to more gates that can basically transform these superposition states or these superpositioned information. Exactly.
So instead of just flipping basically from the one state, let's say arrow is pointing up, to the down state, we can also flip a qubit into, let's say, pointing to the left or to the right, or turning it around a different axis, for example.
Yeah, that's
right?
actually a very, very nice visualization, very nice picture, because what happens is that you start with some arrow direction.
Yeah.
And by applying some quantum gate, you just change the state. So you just change the direction in what your arrow points to. So for example, you just mentioned the Hadamard gate. If you have a qubit that is in maybe the 0 direction, so that means the arrow points up, then you can apply the Hadamard gate to flip like 90 degrees, and then it's
in which direction?
To the right from my perspective, but it does not really matter too much. The point.
I'm just showing the block sphere again, actually, just very quickly. Okay, so I think that's easy to. Oh, I need to present again, but I'm able to do that. I think.
I think the audience sees the same.
Okay.
Yeah. Let me just find it. Yeah, perfect. I just wanted to bring it on again.
Yeah. So what you just mentioned is that in a classical computer, you can just flip your arrow up and down. And now in the quantum computer, by, for example, applying the Hadamard gate, you can flip your arrow from up to the basically this horizontal plane, if you want to say so. That means you can start with a 0 state and just bring it into one of these superposition states by applying the Hadamard gate.
Okay, very cool. And then you can also do things like, let's say I have 3 qubits, and if the first 2 qubits are in on state or something like that, I want to flip the 3rd qubit. All right, I think that's possible. So that's what we can kind of know from
like that's the
classical computing
and or gates. That's how it would be the, like, let's call it classical gates, computing gates, logical gates, plus that Hadamard and C0.
Exactly.
Probably a few more.
Yeah, and maybe if I want to mention, or because you mentioned the C0 gate in the beginning, and we also talked about entanglement, if you have a qubit in the 0 state, for example, and you apply a Hadamard gate and the C0 gate, you only need these 2 gates in order to create this entanglement that we just talked about. So you need 2 qubits, you need a Hadamard gate, you need a C0 gate, and then you can create this magical state, entangled state.
That's exactly how a lot of this sounds.
Yeah, it sounds
really
like
magical,
it, but it's research.
At the beginning, you mentioned that you're doing a lot in software, actually, right? So not so much. Basically, you're not every time entering the freezing whatever cold zone trying to build a quantum computer, basically, but you're actually working at a safe distance to the quantum computer, and you're working in software. So how do you actually program a quantum computer? Let's maybe come to that topic.
Yeah. Currently, what people do if they want to program a quantum computer is they want to design a sequence of these quantum gates that act on the qubits in order to transform the information. So that means that you would write basically a script and just identifying the gates that you want to apply to. In order to do so, there are several, how to call that, like languages, if you want to say so, or frameworks that you can use. I think the most well-known, or one of the most well-known, would be Qiskit, for example, by IBM, but also there's Cirq by Google and Penny Lane by Xanadu. So there are a lot of options. The idea basically is always that you want to identify the sequence of gates that you want to apply. And then you can just do it, for example, in a Python script.
So does every company here have their own SDK and they're incompatible with each other? So if I write something in Cirq, you said, I believe, right, by Google, it would not run on IBM's quantum hardware because IBM requires me to write a Qiskit program.
I mean, in the same, let me take that down the stack once again. So just trying to imagine how that really works. So you have like a bunch of qubits somewhere on a chip, arranged in an array.
Somewhere in a box.
Somewhere in a box, and wherever. There's a bunch of qubits, and they by themselves do nothing, but there is a mechanic, there is something around that would allow to configure how those qubits behave or how they're manipulated through a script. That's the programmable part. How does
Yeah, I think actually it depends a little bit on the framework. I'm not so sure about the single frameworks, whether they maybe also allow access to other hardwares. But for sure, there are frameworks that are more general. So you just write down your sequence of gates, and then you can basically just say, oh, please use this hardware device, or please use another hardware device from different companies, for example. And nevertheless, it will work. So this exists in general. I just cannot.
But let me rephrase my question. So it's not like again, coming from that traditional computing background, I'm that old that I spent time like soldering logical gates and doing chip design and all that. I got that by education, and at some point it's hardwired before it becomes programmable. And it's like those qubits. Are those somewhere in a piece of hardware arranged somewhere? Those gates are coming in how? Like
okay. Okay, so basically, if you have your quantum device, you have your qubits, for example, on a chip. It depends on your hardware, and then you want to manipulate the state. This it always depends on your actual hardware platform. Okay. So, for example, it could be that you can manipulate your state of your qubit by shining some laser. So this is a very simple example. Okay. It's not very accurate. And then what you do if you write such a script is you write down the sequence of gates, and these gates actually can be decomposed into a minimal set of gates. Okay. And your quantum device basically supports one of these minimal gates, which they can implement, for example, by shining on some laser. So you write your script with some gates, then something in the background runs to transpile down this sequence of gates into your minimal gate set. And this can then be executed on your device.
Okay, makes sense. Thank you.
And so I think around the end of the year, last year or so, I was also playing around with quantum computing, and I was running something on IBM's hardware, which I believe everybody can do for 30 minutes per month, I believe, for free, right? So I just highly recommend to do that, actually. And if I remember correctly, every hardware is also different, right? So and I was, of course, having access to some super cheap quantum hardware, which just had maybe, I don't know if it did make sense at all. I think it was something around 15, 20, 30, whatever qubits or so. And I remember not every qubit is connected to each other. So not every qubit, it has a certain architecture, right? So they come in a certain shape, basically, right? And not every qubit can be entangled with another qubit. Yes. You have to find the right qubits that are next to each other, for example.
Yeah.
So that means every hardware by IBM and by Google and whatever, they all have different architectures, and that's why, so you're very much, it's basically like the hardware architecture of, it's like ARM and different architectures, basically, right? So you have to really write a program that fits to the hardware qubit architecture, and so it's. Do you think is there some standardization happening at some point, or will this always be the case, actually, right? So that we basically have incompatible hardware, or do you think at some point we come to a standard quantum computer? Or something?
There is incompatible hardware in traditional computing.
Yeah.
I mean, I think this is still so active research that you cannot really say which kind of design also of the hardware will be working in the end.
So what you're saying is basically the winner has not been chosen yet.
That for sure not.
Right? The winner has not been chosen. That's why there's probably a high level of diversity when it comes to computing hardware for quantum, basically, right?
Yes, but also maybe I misunderstood what you just said. What I understood is that you say basically if you choose to program an IBM hardware, you need to actually tailor your gate sequence to that hardware. And that's not completely true for the end user. So the end user just gives a sequence of gates, and what happens in the background is exactly translating the sequence of gates, which you could give to any quantum hardware device.
Okay.
And then you need to actually decompose it into this minimal gate set, but also making sure that it matches with the connectivity. Or with this, what you just mentioned, that not every qubit can be entangled with the other qubit.
You need to take that into account. Then.
But this happens in the background, actually.
Yeah. Okay. Cool.
Let me try a little bit conscious of time here. We have one or two questions that I guess we still want to talk about. Like we talk about programming quantum computers as it was a simple thing. It's probably not that simple, right?
Depends on what you want to do. If you just want to entangle 2 qubits, as I said before, it's easy. Just take an Hadamard and a CNOT.
Tick the box, got the T-shirt.
I should print myself a T-shirt. Hadamard and CNOT.
Exactly.
Just to be.
Yeah, but exactly what you said. So if you really want to write a program that can simulate a complex system, for example, it's not easy. Otherwise, I wouldn't have this job. So this is exactly what a lot of researchers, also in the software or on the numerical side, do. We try to find out ways to build such a script, basically, such that we can simulate systems or solve optimization problems. And that's still not easy at all. Yeah.
Okay, that's interesting, in particular with all that Python libraries available to program that. It seems so easy, but it's apparently not something for the everyday life, right?
Yeah, I mean, if you know what you want to program, it's easy.
It's very specific.
Yeah, but you just, I think the difficult part is thinking about the algorithm.
Okay. With that, let's move to our typical last question. We are trying to be the innovative guys, and we always look for the future.
We're trying really hard.
We're trying really hard. We fail most of the time. You're a researcher, you know that feeling. Right?
Yes, I know it very well.
At your work at Technical University, like trying to take that look into the future, how are the next couple of years going to look like in quantum computing? We started the conversation with major announcements from major companies, all the hype that we saw that brought us back to quantum computing. So that's been a thing of last year. What's going to happen the next couple of years?
Or in other words, basically, will we no longer talk about AI and AI agents and agentic AI because there will be some breakthrough in quantum computing this year?
That's
that would be very, very optimistic.
$1 million question.
What do you know?
We don't know.
Well, I think I tend to be very hesitant with these kind of questions. Like, I do not like just putting out some numbers because it's really also not very easy to answer. So I cannot really tell you, oh, in 5 years we will have a chip that works with this accuracy or with this number of qubits. It's very difficult, especially for me, since I'm not in the hardware side, to estimate this. But maybe I can tell you a little bit about what we here in Munich do for this effort. Because actually in Munich, we have a very, very active quantum environment, not only at the university, but also in collaboration with maybe industry partners, etc. So what we have in Munich is something we call the Munich Quantum Valley, which is an initiative that brings together a lot of research institutions and research groups in general that are interested in quantum. So I just looked it up a couple of hours ago. I think it's really more than 60 groups or something.
Wow.
So it's really an active environment here, which is great for us researchers. And this Munich Quantum Valley really wants to approach the overall quantum computing question of how to build a quantum computer. So there's active research in the hardware section, where we also research different hardware platforms. So we do not only focus on, for example, the superconducting qubits, which we also do, at the Walter Meissner Institute, but there are also efforts in building a quantum computer using neutral atoms, for example, at the Max Planck Institute for Quantum Optics. And also we are interested in ion-trapped based quantum computers, another hardware platform. And in addition to that, we also want to, of course, besides researching all these algorithms, provide a software framework in order to program all these quantum computers. So actually, I'm not very much involved in these areas since I really work on the algorithmic sides. But it's basically the idea of this Munich Quantum Valley that we focus on both hardware and software, and also be able to in the future deliver this quantum computing or the quantum devices to other people who might need to use them.
Okay, wow.
Okay, just to sum that up, so you're saying it's difficult to make a prediction, but we will have lots of opportunities to talk
That
again
for sure.
in the next
That
couple
for
of
sure.
years. Okay.
And we don't know exactly how many, but it's in between zero and one and multiples of that, basically, I would say.
Exactly.
All right. Thank you, Isabel.
Thanks a lot.
Thank you so.
too.
Thank you very much. That
Amazing.
was really brilliant, and I hope it really would shed some light on a lot of these concepts that are quite magical, I think. Yeah.
Yeah.
Thank you so much. Yeah.
See you
Thanks
soon.
everybody for watching. Very
Thanks.
cool.
Ciao.
Bye bye.
Ciao.